Software engineering is an exercise in stacking mental models. Every application relies on layers of abstraction designed to hide the lower-level complexity beneath it. Code objects map to table rows, rows map to bytes on disk, and bytes map to microscopic electrical charges. Choosing a database commits you to a specific way of thinking about your domain. It is the selection of the foundational mental model that will dictate your architectural constraints. Modern data architecture is dominated by three core geometries: the relational grid, the document tree, and the graph web. Each shape makes distinct mathematical assumptions about relationships, whether through intersecting axes, downward parent-to-child flows, or omnidirectional networks. There is simply no universally optimal model. Designing a successful system depends entirely on objectively mapping your application's specific access patterns to the correct underlying geometric shape. The relational model, proposed by Edgar Codd in 1970, organizes data into tuples, or rows, within relations, which we know as tables. Instead of relying on direct memory pointers, relationships are formed strictly by matching values across columns. This model has dominated the industry for 50 years because it maps efficiently to the uniform many-to-one and many-to-many relationships found in standard business transactions. Orders have customers. Transactions relate to accounts. The grid handles this seamlessly. But modern applications are typically written in object-oriented languages. When these objects interface with a relational database, they create a severe architectural friction point known as the object-relational impedance mismatch. Object-oriented code relies heavily on nested collections, types, and inheritance. Relational databases strictly require flat, two-dimensional structures. To save an object like a product containing nested arrays of tags and categories, the system has to shred it. The single object breaks apart into discrete data blocks, cascading down into separate tables linked by newly created foreign keys. The true cost comes during retrieval. Reading that object back into application memory requires either multiple sequential trips to the database, the classic N+1 query problem, or complex, heavy join operations to stitch the shattered pieces back together. This mismatch also introduces the complexity of cache invalidation for derived data and makes polymorphic associations, like an attachment belonging to either a post or a comment, awkward to express. Forcing nested, self-contained domain data into flat relational tables bottlenecks system performance through sheer mapping and retrieval overhead. If your domain is characterized by self-contained tree-shaped data, the document model provides an immediate architectural solution. A standard professional resume is a perfect example of inherently nested one-to-many data. You have top-level personal info, an array of past roles, and lists of specific bullet points under each role. In a relational database, assembling a single user's resume requires a four-level join across distinct tables for users, experiences, bullets, and subbullets. This diagram shows the structural comparison. A document database bypasses the join logic entirely. It stores the exact same data tree as a single, cleanly formatted JSON block. This creates a massive hardware-level performance benefit. Instead of the disk read head jumping frantically between different table sectors to gather the relational data, it performs one smooth, contiguous sweep to read the entire JSON document at once. The non-relational movement of the late 2000s heavily marketed document databases as schemaless. That is an architectural fallacy. The schema always exists. The difference is when it is enforced. A relational database uses schema on write. Similar to static typing in programming, the database rigorously enforces the structure at the exact moment of insertion, rejecting anything that doesn't fit the predefined columns. A document database uses schema on read. Similar to dynamic typing, the database accepts arbitrary data. The application code assumes the full responsibility of interpreting that structure at query time. This makes data evolution and application migrations trivial. You simply write the new shape and update the read code, but you sacrifice early error detection and strict data consistency guarantees. Furthermore, document stores severely struggle with highly interconnected data. Without native join capabilities, maintaining links between separate documents requires data denormalization, forcing the application layer to manually keep duplicate data consistent. The document model is an explicit trade. You surrender relational flexibility and strict integrity in exchange for raw read performance and schema agility on isolated data aggregates. Some data is so heavily interconnected that the relationships themselves are as varied and complex as the entities. This is the domain of graph models. In a property graph, data is structured into vertices, or nodes, and edges, which act as the relationships. Both can independently hold key value properties. Graph schemas offer ultimate flexibility because absolutely any node can connect to any other node via any type of edge. There are no rigid table constraints dictating how entities can interact. The physical shape of your data strictly dictates the language required to query it efficiently. Try finding a friend of a friend of a friend using standard SQL. Querying variable depth relationships requires recursive common table expressions, which are mathematically awkward and computationally expensive for deep chains. Graph databases solve this using declarative query languages, like Cypher, which provide an elegant syntax for deep traversals. Look at this query designed to match a path starting from Alice and traversing a nose relationship. By adding a simple variable length indicator, this syntax instructs the engine to traverse an unknown number of relationship hops, returning anyone connected to Alice through any length of chain. This illustrates how declarative query languages operate. The engineer specifies what pattern to find, while leaving the how, the exact traversal execution path, entirely up to the database's internal optimizer. Contrast this with imperative data frameworks like MapReduce, which force engineers to hard-code the exact step-by-step execution path. This limits the engine's ability to parallelize work or automatically apply optimizations when new indexes are added. When application logic is driven by deep, evolving relational pathways rather than flat aggregations, graph models paired with declarative languages provide the most efficient path for representing that complexity. Looking across modern system architecture, it is clear that no single database model won the industry wars. Data shapes are inherently diverse. The current standard practice has evolved into what we call polyglot persistence. This table outlines the approach: deploying multiple specialized data stores within a single distributed system. You use the relational grid, the document tree, and the graph web side by side, each independently serving the access patterns they handle best. At the same time, major database vendors have spent the last decade aggressively converging on these features. Relational databases now natively index JSON document columns, and document databases have built out SQL-like lookup joins to handle relationships. The hard boundaries are blurring. The core lesson of the logical data abstraction is this: heavily optimizing a schema for one specific query pattern inherently degrades the performance of others. The honest architect accepts this trade-off, but the logical shapes we query against are still just an abstraction. The real physical constraint lies one layer deeper. Regardless of whether your query language sees a flat table, a nested tree, or an interconnected graph, the database engine must ultimately translate that geometry into linear sequences of bytes on a spinning disk or flash drive. Mastering logical data models is only half the architecture battle. The next challenge is understanding how these abstract geometries map down to physical storage structures, like B trees and LSM trees.